We have here what looks like a pretty ferocious polynomial to factor. It's a 5th degree polynomial. And what's going to be a little different about this one, this isn't just a longer problem. This is going to be different than other rational roots synthetic division problems before that you've seen. Certainly we need to have several skills, rational roots theorem and synthetic division. I'm assuming you know those by now. This is not an intro video. I also assume that you've been over the complex conjugate root theorem and how to solve quadratics generally. And I'll explain some of these briefly as we go through this. But let's start off with what does look like a very clear rational roots theorem part. This p's over q's thing. I want to know what are all the possible roots. Not the actual roots, just the possible ones. So what you do is you say all the factors of 27 divided by all the factors of 1. And that's pretty easy because factors of 1 is a limited set. So we just say, really, what's the factors of 27? It's 1, 3, 9, and 27. That's it. Now we have to remember that plus and minus, so we really got a few more. -1, -3, -9, -27. So this list is really not that long. Oftentimes you might have 16, 20, 24 possible roots that you have to check. Not that you should ever be checking that many. There's usually a hit in these first several. So I want to focus your attention on 1, -1, 3, -3, right? These are the first ones that we're going to be checking. And there's almost always a hit in one of those first ones, if your math teacher's a nice person and has designed it well for you. So let's get going with this, and there's going to be something interesting that happens in this problem pretty early on. So I'm going to set up my synthetic division bar, like so, and I have my coefficients of that polynomial, 1, -1, 12, -12, 27, -27. Okay, you can see those are the coefficients of these terms. And I'm just going to start with the first number on that list of p's and q's that I looked at. We're going to start with the number 1, I think. So we just run down through our synthetic division. 1 times 1 is 1. Add these up, you get 0. 1 times 0 is 0. Add these up, you get 12. 1 times 12 is 12. Add these up, you get 0. 1 times 0 is 0. Add these up, you get 27. Multiply again, we're at 27, and now we're at 0. So normally at this point, I would say, great, keep on checking, right? Let's try 1 again, and then if that works, great, we factored out another root. If it doesn't work, we move on to another guess, like -1. Got pretty lucky getting the first one on this one. But there is something happening here that I want to point your attention to. See these zeros right here? Kind of an interesting pattern. Let's just pause for a moment and look at what the factored form is of this polynomial. So I just pulled out an x minus 1, okay? Remember, that's coming from this x-intercept, this root which we just found of 1. That comes from a factor x minus 1. So there's my factor that I pulled out. What's left, and I'm getting this from this set of numbers right here, that's the quotient coefficients. This is going to be x to the 4th plus 12x squared plus 27. Okay, now I know I can factor this. I suspect I can factor it more, right? This is what f of x is. Okay, I could write it in partially factored form, but remember I want it fully factored and I want to know all the roots. And I suspect there might be up to 5 roots, so we've got a long way to go. But as you look at this, you should remember any chance you have to stop doing rational roots and synthetic division should be taken. If there's any other way to factor this, we should go for it. So I want to remind you of something. It should be an old skill. It's called U substitution. And if you look at what I'm writing right here, notice that I've changed x squared to u. And now when you write it this way, u squared plus 12u plus 27, well, that looks like a plain old quadratic. In fact, this is why we call this quadratic form. This is not actually a quadratic right here, but it has the form of a quadratic because you have a pattern of exponents and a trinomial. So I'll bet we could factor this pretty easily. You've been through factoring before, I hope, at this point. So two numbers that, let's see, multiply to 27 but add up to 12. Well, I get 3 and 9. Okay. Now remember that I'm not interested in u. What I'm really interested in is x squared. I just did the u substitution to help myself through it. What we've got here is x squared plus 3 and x squared plus 9. Okay, now, remember what the problem asked for. It wanted, and I'll point this out again, it wanted fully factored form, which is what we have right here. See, I took a shortcut. We factored it real fast from the quartic level, this 4th degree, without even using any more synthetic division. That's fully factored form because what I have here, and pay attention, this is linear or irreducible quadratic factors. And that's what I have. Now, in terms of the roots, it's not quite done yet. We have to set each of these equal to 0 using the zero product theorem. Okay, so the zero product theorem says a few things. It says x minus 1 equals 0. Okay, if we're looking for solutions to the following, right? Setting the whole thing equal to 0. We're looking for solutions. So the first root is easy. X equals 1. No problem. We've done that a bunch of times. This next root might give you pause for a second when you say x squared plus 3 equals 0. Well, you can solve this like an equation. You say x squared equals negative 3. Take the square root of each side. What do we get? X equals plus or minus square root of 3, but that's not all. Because that's a negative number, this is actually plus or minus I times the square root of 3. This is imaginary. It is okay to have imaginary roots. That's often something that happens when you're doing polynomials. Not every single root is going to be real. Now this last one over here, we have x squared plus 9 equals 0. So in this case, that would be x squared equals negative 9. That means x equals plus or minus the square root of 9, plus or minus 3i. Okay, so there are my 5 roots. 4 of them are imaginary. 1 of them is real, like I've written here, and that is the end of the problem. The shortcut happens because unexpectedly we got this thing into quadratic form. So we took that off ramp. And I want to remind you guys, any chance you can to not finish up synthetic division with all the rational roots stuff, take that chance. Okay, this is a much quicker way of solving the problem.